Our speaker this afternoon has done many, many things, I think it's fair to say. I think you've had a varied career. Came to the ISS in 2003, did undergraduate here at Sydney, did a PhD at Caltech, doing well so far, stayed in America, worked at NASA twice, I know, and we should have a t-shirt printed up. Yes, I used to work at NASA. I left NASA too. Stopped working at NASA, worked at Hyperloop for a while, which sounds bananas, to be honest. One of those technological problems that seems like a really good idea until you come up against the fundamental problem that means it's not going to work, and maybe that's where that is. But worked there and solved an enormous number of problems. And then, well, I'll let him tell the rest of the story, but is now working for a really interesting person himself, with his own startup company, doing some fascinating and hopefully really huge things involving carbon dioxide and really cheap solar. Would you please make him very, very welcome, Casey Handmer.
Thank you so much for that suspiciously grudging introduction. It's actually incredible to be here. It's kind of a walk down memory lane in many ways. And actually, I was just thinking, as you said, that most of these people were not born in 2003. I have schoolmates who have children who are older than you. Yeah, that's kind of wild. They could be grandparents soon, I guess. I'm not that old. Can everyone hear me? Yeah. Right. If you can't hear me, just gesticulate wildly and we'll figure it out, okay? I'm going to do my best. I'm actually accustomed in the United States to being hard to understand because I speak quickly and in a strange accent. But here, at least, most of you should understand at least the Australian parts of what I say. Anyway, let's get cracking. We're just kind of going to meander along here for a while. Depending on how the talk goes, we can take questions as we go, and we'll have time at the end for lots of questions too. But first of all, and to recycle a joke given by Professor Virginia Trimble, who spoke 20 years ago at ISS, this slide exists to remind me what I'm here to talk about, and on a bad day, what my name is. All right, let's see if I can make this work. So close. All right. So here's a rough outline of what we're going to talk about. And have any of you played with Midjourney yet? Have you played with Midjourney, the thing that generates images? Oh, yes. All right. So that's where this image comes from. I asked it to depict the radical future for humanity expanding through the stars or something. But that's kind of what we're here to talk about. So today we're going to talk about a bit of my background. I'm not going to bore you all with my biography forever, but we'll go through a little bit of detail. And we're going to talk about energy, specifically energy that we use to do stuff, as opposed to just energy in the universe. And we'll have time for questions. Then tomorrow, I'll delve into greater detail into the specifics of what my company, Terraform Industries, is doing. And I have a few stickers here, which I brought from the United States. So if you answer a particularly good question and you want a sticker, I can give you one. I know Dr. Carl used to hand out T-shirts. I don't know if he still does, but
his budget's not so big anymore.
Oh man, I'll sponsor it. Okay, so as I said, it's a real honor to get to return here after 20 years. And I get to indulge my interest with a group of genius young adults, you guys, from all around the world. And yeah, this is me. There. So this is out the back of the old building before they built this building. There used to be grass there. And just to kind of blow your minds, in 2003, we didn't really have usable cell phones. We had Nokia 3210, which is indestructible, but we did not have smartphones. We didn't have the mobile internet. We didn't have reusable rockets. We didn't have ChatGPT. I had to talk to other people. So, behold, the living relic before you all. I have gray hairs now. But actually, well, we didn't have Facebook back in those days, so I kind of lost touch with a lot of people. But the fellow who's standing behind me up here, that's Dion Ponsini, and he lives in the United States now, and we're good friends still. We met here. And in fact, he invested in my company. So,
that's a friendship.
well, he asked me nicely, and I said, okay. And he said it wasn't very much. And the reality is, the quantity that he invested will pay for one internship, which is not nothing. It's a whole person who comes to work with us for 3 months, and they get to start their career and do stuff. So So every little bit counts. And you'll see tomorrow why we need money. It's kind of expensive. All right. All right, there we are, all zoomed in. So I looked at this picture and I was suddenly afflicted with nostalgia. And really the algae part of nostalgia, which means pain for the past. And I had this sense of affinity with my 15-year-old self. I had no idea what was going to happen, what I was going to do, what my life would turn out to be like. I really, at least prior to the International Science School, had not really spent much time with people like me. Didn't really know where my place was in the world. I was kind of confused about some stuff. Didn't really, working stuff out. And so that's the secret second agenda of this talk, which is to assure you that your life and career can take unexpected twists and turns, and it's all okay, and that the stuff that sucks now will get better. The stuff that seems all-consuming right now will often turn out not to be a big deal later on. Girls, boys, all that kind of stuff. That said, you're in a very special time in your life. You're forming lifelong passions. You may not be aware of this right now. You may like that perspective, but you'll get it later on. I really have 95% of the music that I enjoy today, I discovered between 15 and 20 years old. All my oldest friendships I formed during this period. I don't really hang out that much with people I met beforehand. And also, you're in this time in your life where you have the time to knuckle down and get really good at calculus. It's like you can still learn stuff at any age, right? But if there's a really kind of huge sum of knowledge that you want to master, now is the time to get cracking. Your brain will never be as fresh as it is now, and you'll never have the time to really sit down and read books and so on. I have time to do other things now. I have different resources. I can do different things that I could do back then, as I will talk about. But I really don't have the luxury of, taking 3 months and just mastering a course of something anymore. All right. And then, of course, the disclaimer. This is Midjourney's best approximation of what my ancestors looked like 30,000 years ago, who are, of course, genetically essentially identical to me today. Humans don't evolve very much over that period of time. And so I need to preface this talk by saying that I'm going to say some weird stuff by the standards of things that you've heard from your lecturers over this course of this event. And all the advice that I will give you, if I give you any advice, will contain path dependence, right? Because I've only lived my life. And I am, obviously, a poorly evolved ape, like all the rest of us. A lot of this is just my opinion. And as I think I said in the interview, do not feel obliged to validate my catastrophically poor career choices, which I've gotten very lucky, right? I've survived several attempted self-immolations by repeating them, right? You take your own path, do your own thing. But the whole point of this exercise is to ask questions and to kind of try and get a little bit less stupid over time. So, why are we here? Anyone want to yell out something? Why are we here? I mean specifically, why are we here at the International Science School?
Arbitrage.
Okay.
Because I got a pain here.
Okay. Yeah, physics. Okay, the reason we're here is that the 115 odd people in this room have been assembled by a persistent meme, and this meme goes back thousands of years, that believes that there's value in searching for talent, seeking out talent and developing it, to lead the next generation as part of social reproduction, right? And that's a huge honor. It's a huge privilege to be selected as someone who your elders think might turn out to be okay. It's also kind of a responsibility because, look around and there's a good chance that people in this room will be a huge fraction of the movers and shakers in Australia and other countries in the next 10, 20, 30, 40, 50 years, which is building all the cool stuff, right? Like cities on Mars and whatever, look around. So it's kind of a bit of a responsibility as well. Now, every generation has its challenges, and I found this amazing list the other day on the left, written down by Robert Boyle, who was a famous scientist, an early scientist in the 1600s, a contemporary of Samuel Pepys and I guess Isaac Newton came along a little bit afterwards. And he discovered a bunch of stuff to do with gases. And I just have this list of things that he wrote down in his journal. I guess it must have been after 1662, because he mentions tea, which I don't think appeared in Britain before then. And it's kind of neat. I put a little line next to all the ones we've solved, at least solved well enough for his purposes. Right? There's some stuff there that's kind of mysterious, but at least as far as he's concerned, if he saw what we've done, he'd be convinced that we've solved flying. And we've solved submarines and scuba systems. We've got antibiotics and surgery. We've figured out metallurgy and radioactivity. We figured out how to make armor light and extremely hard, which is about halfway down there. Let's see, there. Right, we have Kevlar and so on, but we also have firearms, which didn't exist in a modern form back then, and we have nuclear weapons, which is a bit of a downer for personal armor at least. Parabolical and hyperbolical glasses, that's optics. Right? We solved that problem. I mean, we're still getting better at it, but we've launched the James Webb Space Telescope, so like we're doing all right on that front. A practicable and certain way of finding longitudes and the use of pendulums at sea and in journeys and the application of it to watches. That's a big deal, right? People have been sailing ships across the oceans for almost 200 years by the time he wrote this list down, and they were still routinely crashing into rocks because they couldn't figure out how far east and west they were, because even though they could tell what time the sun came up, they couldn't compare that to the time back home in England or wherever, so they didn't know how far around the world they were. There was a huge prize worth millions of dollars in today's money to solve this problem, but it was not really solved for hundreds of years after Robert Boyle. And Galileo's contribution around this time was to figure out that you could build a primitive clock by measuring the position of the moons of Jupiter with a telescope, which he invented for that purpose, right? It's kind of cool. But nowadays we have GPS satellites, so like, I think you would probably agree that we won that one, which is pretty neat. I worked on GPS at JPL, by the way. That was what I got to work on. They didn't let me work on the fancy Mars stuff mostly. I just got to work on GPS. A ship to sail with all winds and a ship not to be sunk, up to a constant in the Titanic. I think we've nailed that one. And then freedom from necessity of much sleeping, exemplified by the operations of tea and what happens in Mad Men. I mean, amphetamines exist, but up to a constant. I'd say, like, actually, here's some potentially dangerous advice. Obviously, listen to your doctor, but people who go into academia and medicine and so on often feel tempted to use things like Adderall if it's not medically indicated to defeat sleep. It's usually a false economy. Perpetual light, okay, we're under it right now. That's pretty cool. And then, I don't know, some other cool stuff there. And then here I have a list, you probably read it by now, because I speak slowly, of my list of stuff. And it's not particularly complete. I just jotted these down the other day. But I have a reasonable expectation that we'll solve at least half of these in our lifetime. So, and we'll cover some of these in today's talk, but we need arbitrarily cheap solar panels. We need to figure out what radioactivity is for. So who here reads XKCD? It was kind of popular when I was in school. All right, some people are. The joke is, how are we going to power the spacecraft? We could just use this power orb. It's just this like chunk of metal that emits power. And they're like, nah, it doesn't exist. How does that work? And but it just emits energy, and it's true. Plutonium-239 just glows for like 100 years for no reason. Right? I have a little piece of tritium that hangs off my light in my bedroom in a vial. It's not dangerous, and it'll just glow for 10 years. Right? It just, like, what the hell? What's this for? We don't know. Like, we made nuclear weapons and we made nuclear power plants, which are like glorified steam engines. I mean, physically speaking, radioactivity is quite clearly for interstellar travel. Right? It's to give us the power to travel to other stars. But there's work to be done there. Right? We've understood it for 100 years, and we still don't really quite know what to do with it. Control the carbon cycle, we'll talk about that. Control the water cycle, weather control, restoring select environments. Immortality, I mean, that's up at the top of Robert Boyle's list as well, the prolongation of life and the recovery of youth. We've done all right in the last 100 years. We've tripled life expectancy, but we're not quite there yet. Speaking of which, I'm 35, so 100 years ago, half the people born in the same year I was would be dead by now. Immortality, electric planes, supersonic passenger planes, zeppelins, atomic scale 3D printing, tunnel boring machine mining, compact manufacturing. So actually, there's an interesting point, which is, again, one of the themes we'll come back to here. And it's somewhat unfortunate, but particularly in Australia, that Australia does almost no manufacturing anymore. But it's how we get stuff. Right? Everything in this room, everything we interact with is started off as rocks on the ground and somehow got turned into useful devices that we use and take for granted. Like, this thing is more magical than the Harry Potter wands that I read about when Harry Potter was first published, because I'm that old. This thing has practically every element ever discovered in it, doing all kinds of weird and wonderful things. It's a supercomputer, right? This phone is as powerful as the best supercomputer available 25 years ago. And yet, in Australia, we just assume this stuff comes from somewhere else, Candy Mountain or something. But there's a problem that this technology we're so dependent on cannot be produced in an economy with fewer than 100 million people. And Australia is obviously much smaller than that, which somewhat makes us vulnerable. right? And it would be super neat if we could figure out how to do it with 10 million people or 1 million people. It'd make it a lot easier to build a city on Mars as well. There's no intrinsic reason why it can't be done. You're taking atoms in one form and arranging them in another form. But for the time being, at least, if you want a full industrial stack, right, the ability to make anything from pencils to microwave ovens to supertankers, you need 100 million people. So that's a problem to be solved. Starship, planetary bases, terraforming, antimatter propulsion, better AI. This one's moving pretty quickly now. Fusion, brain-machine interfaces, ambient robotics, time travel, post-scarcity, and transhumanism. I think time travel may not arrive before I'm dead, but if we solve immortality, then who knows? So are there any particular challenges that I've not mentioned that you find interesting, that you'd like to shout out? I'd be interested to know. Like big things. Do you have any ideas?
I think you pretty much got them all. I'm
hope not.
curious about zeppelins.
Yeah, we'll come back to that.
Yeah, I thought
Yeah.
Yeah.
Yeah, why travel at high speed at high altitude when you could travel slowly at low altitude? So I mean, like, hopefully, at least for most of you, you see something on that list and you're like, you know, I could see myself making that my life's work, right? And it will be the life's work of probably tens of thousands of people to solve any one of those problems. Certainly if you think about reusable rockets, which were science fiction when I was a kid, and now just like in the last week, SpaceX has launched 3 or 4 rockets, which is pretty insane. That was the life's work of tens of thousands of people really to make that happen. Unbelievably tough problem. Huge vision, right? But it could be done, and it was done. In principle, it could have been done 50 years ago, but it was easier now, I guess. All right, next. So I'm going to talk a little bit biographically here about how I've ironically wasted half my life, assuming I live to 70, which is, we'll see. And so after I did the International Science School in 2003, I did Space Camp and I did Physics Olympiad. I wasn't able to find any good photos of that, unfortunately. And then I did the usual academic track and some other fun stuff along the way. So we'll run through these fairly quickly, and then I want to give you an idea that like cool stuff can happen. At least it happened to me, so it could happen to you. I certainly didn't plan most of this stuff, right? It just kind of opportunity came along and I jumped at it. So this is my office, which is over in the building next door, and I lived here for the better part of a year, actually just over. I didn't actually like sleep there mostly, but I spent easily more than 12 hours a day in this room, 7 days a week. And the people I sat with on either side and opposite are still good friends today. Right? We kind of grew up together in a way. And the first day I sat down at this chair, there weren't holes in it, and I didn't know how to program computers, and I didn't know how to solve real-world problems, and I didn't know how to do research, and I hadn't published any papers. And the last day I sat in that chair, about 18 months later, I'd done all those things. Right? I learned how to do all those things sitting there, and you can see just the giant piles of detritus and crap all over the room. In fact, that's a slack line, which we used to hang up on trees, which are no longer, I think they're pretty much under the floor where we're standing, actually. Hang up a slack line and go and try and not to break our arms too much. Yeah, so in some ways, like this is, when a bird hatches and it looks back inside the egg and goes, that's weird. I look at this and I'm like, that's weird. I kind of became a different person sitting there. But, from humble origins, I guess. Oh, hell, it looks like I'm using Microsoft Outlook. It's desperate. They eventually let me out. I got to graduate. I don't know if they still do robes. I hope so. It's kind of neat. And then I went traveling for a while. So I haven't updated this map in a while, but I haven't got to travel a whole lot since I was younger. And again, at your age, if you're inclined to travel, now's the time to do it. It doesn't get easier when you get older. You get richer, but you don't have as much time, and your pain tolerance decreases. And so here's a photo of me at the eastern end of the Trans-Siberian Railroad in Vladivostok in Russia on 3 separate occasions, in 2006, 2009, and 2016. And it looks like I got more handsome, but really cell phone cameras just got better. And that 9288 is the number of kilometers from Moscow. So that's kind of neat. You can go off and travel. And I would say here that you should not take it for granted, the fact that people here from particularly the Western countries whose passports are regarded seriously are able to travel independently at 19 years old, like basically kids, in safety, comfort, relative peace, relatively low risk of harm, essentially anywhere in the world. And most of this trip I did on like $10 a day or less. It was not the case in the past, right? It was not that long ago, if you read George Washington's memoirs, that like just going to the next door town could kill you. right? Or you get attacked by bandits on the road, or locked up by prison guards or like border guards or something like that, right? It's not always the case. And actually, unfortunately, Russia and the West are in conflict now in a way that they were not 20 years ago. But if you're hell-bent on it, you can still travel to Vladivostok if you really want to. So don't take it for granted. All right, then I went and did my PhD at Caltech, which is in Los Angeles. It's pretty close to JPL. If you've ever seen the show The Big Bang Theory, it's set there. And as you can see, it's a different continent, different hemisphere, but same office organization principles. Just keep piling stuff until they let you out, which they eventually did. And again, I'm still good friends with the people in this office. I spent 5 years, or 4 years roughly in that chair. And the man who sat next to me is now a professor of physics at Santa Barbara. And I played a small role in introducing him to his now wife. So that was kind of cool. And I don't know. Like, I went in there at 23 and I came out at 28. And it was, oh, there's a unicycle, which I didn't learn to ride until 2021. But I learned to ride. It's easier when you're younger. Do it. But yeah, I studied gravitational waves, which are distortions in space-time caused by black holes orbiting each other and colliding, which sounds straightforward now that I say it. But there's some kind of gnarly technical issues that I had to deal with. But I eventually solved it and wrote this paper called Spectral Characteristic Evolution, a New Algorithm for Gravitational Wave Propagation, which I will not bore you with the details of because it's insanely technical. But if you're curious, it's on my website. You can download it and read it. I don't really remember the details anymore, but the journal article that published it thought it was so cool that they asked me to write a feature for the journal called CQG+. It's not exactly Nature, but whatever. So I got my advisor, Professor, actually he wasn't Professor, Dr. Geology here, and our swords. We had a sword fight because that cross shape is a common diagram in general relativity for the light cone. Who here's heard of a light cone? Okay, some of you. So the light cone is this idea that if you have space on the horizontal axis and time on the vertical axis, and the speed of light is the speed beyond which nothing can go, that from our point here in space and time, there are places in the universe that we cannot get to, no matter how fast we go. It's outside the light cone. But everything we can get to is within the light cone, which is inside this volume here. And obviously, it's a three-dimensional cone that is expanding outwards at the speed of light, which is roughly equivalent to 1 foot per nanosecond. So that was fun. It's not every day you get to sword fight your advisor, but he was good-natured about it. And then I finished the PhD, and there was an unsolved problem, and I eventually woke up one day and realized what I'd done wrong and solved the problem. And we put the band back together and wrote the second paper, or the third paper, actually. And they liked it so much they wanted to write another feature on it. But I wasn't there anymore. Baylor had left academia. What were we going to do? Well, Jeffrey Winnicor was I think the editor of the paper or something of the magazine, of the journal. So we co-opted him because he had to do some math for us. And we took the old picture and my sister Annie photoshopped this for us. And we put a picture of Jeffrey in there as the evil emperor, Palpatine. And then those green squiggles are the waveform of the first gravitational wave ever detected by LIGO, which resulted in a Nobel Prize a couple of years later, which actually, that was detected. It was September 14, 2015, which was the same day I left Caltech. So it was kind of bad timing, academically speaking. But and then the picture in the background is a rendering of what two black holes in the process of merging would look like. And this is kind of neat. It's kind of obscured by the lightsabers, but please don't sue me, Disney. This black hole here is twisting space-time so much that we get an image of this black hole over here as well. This little bean hanging out on the side is an image where the light has gone from this black hole, it's shot around the back of this black hole, and then it's come back out towards us. And then there's this circular feature here, and everything inside of there, the light has gone around these pair of black holes once, and then come back out again, which is, if you've seen Interstellar, similar kind of sneaky stuff goes on there. Yeah, if you're close enough to see this happening, tweet it quickly. It's not going to go well, but we can simulate it, which is kind of neat. All right, so while I was at Caltech, Caltech has a geology department, which is regarded as one of the greatest around, and I was very lucky to help them out. I personally don't drink alcohol, which I would actually encourage as a life choice. It does slow you down a bit, but the geologists love drinking, and they're always driving out to the desert to look at rocks. And so they needed a designated driver, or as I think they call it here, a deso. And I was happy to oblige because I didn't have a car, and I like to get out and look at rocks. So I got out and looked at rocks, and I'd just like to point out a couple of things here that I think are thought-provoking. So this is how you don't walk across lava in sandals. This is a lava lake that I jumped a couple of fences to have a look at in Hawaii. This is a volcano in Vanuatu that I went and had a look at. It's actually a selfie, but you can't really see my face there. This is the bottom of the Grand Canyon. So the rocks here, this layer of rocks here, are about 460 million years old, which is somewhat older than the oldest dinosaurs. They're about the same time as the Cambrian explosion. And then the rocks down here, the Vishnu basement schist, is 1.4 billion years old. So this gap here is a gap in the geological record 1 billion years long. Right? The universe is 13 billion years old. So like 6 or 7% of the age of the universe just kind of disappeared here. And essentially what happened is that above this, or should I say below this, these rocks formed, and then this part of the crust went up and eroded. And it went down and up and down and up, but overall it eroded more than it deposited for 1 billion years. And then it started to sink again. And all these rocks essentially formed at sea level from here up to a mile, a kilometer or so higher up, which is how rocks form. The land sinks and the rocks wash into oceans and stack up, which is kind of neat. So as you climb out of the Grand Canyon, in addition to cursing your luck and your bad ideas because it's kind of a hard walk, you can also look at geological history like a book going from 400 and something million years ago to about 150 million years ago. And then a long time ago now, I climbed up Mount Whitney, which is about 4,500 meters. It's the tallest mountain in the lower 48 of the United States. And of course, once you're on the summit, you change into your dinner jacket and bow tie for the summit photo, which was fun. And then this is in Russia somewhere, so that was fun. Rocks are cool. This is a theme we shall return to. Flying. So it turns out that with less time and money than it takes to drive a car, in both Australia and the United States, you can just learn to fly planes and fly them. So in the United States, at least, you can get your pilot's license with 40 hours of training, of which only 20 hours has to be one-on-one instruction, which is kind of crazy. And I didn't have much money, so I did 20 hours of one-on-one instruction. There's a picture of me in the middle flying a cheap and cheerful Cessna around the place, looking out the window at stuff. And of course, if flying in planes is not your style, you can always throw yourself out of a plane with a backpack and a parachute and give that a go. And you can use your appendages as wings. You don't fly quite as well, I will say. Fall pretty quickly. Oh yeah, so here's cool. A thing that I did back in the day, which is if you hang out with cool people long enough, sooner or later they'll ask you to help them with their art project, and then you help them out, and then they're like, hey, come to this giant party, it's 50,000 people in the desert, and we're going to put the Tesla coil up on this giant stand thing and connect it to a keyboard, and you can play music on it. So with any luck, it'll work. That's me there. Oops, I was going to say that's enough, but I don't want to bore you too much. It's I mean, there's no reason you can't do this, right? Like, in principle, the ancient Greeks could have built one of these things. Not the music part; that would have been a bit tricky, at least the MIDI connection. But they had the technology. They understood how to make low resistance copper wire. So yeah, that's kind of fun. Just read a manual and try not to kill yourself. I should say that it's hard to describe just how loud that is. We don't really get the full effect here, but this is a very noisy place, right? It's a huge dance party in the desert. There are lots of music going on. This is Hyperloop 1. So I was a levitation engineer there. It was my responsibility to figure out megalith stuff, and that was kind of cool. If people have questions about that, we can come back to that. Then I got to go to JPL. So day one, bright-eyed and bushy-tailed, standing up by the meatball. 4 years later, last day, kind of shell-shocked. I mean, to be fair, in the interim, I'd had 2 kids and COVID, but it was a good time. This is one of the high bays, which is a giant clean room where they're building the Perseverance Mars rover, which has since landed on Mars. And you could just walk down there anytime you liked and stand in a little enclosed windowed room and watch all these people in their white coveralls putting stuff together. And then just off to the right here, out of shot, they were building this part, which is the sky crane, which is the part that lowers the rover down onto the surface of Mars. And here's an actual photo taken by the Mars rover as it was being lowered onto the surface of Mars by this alien spaceship, right? Like the conspiracy theorists say that JPL's got aliens. They don't have aliens, but when we fly to Mars, we are the aliens. Here's an alien spaceship landing on an alien planet. And these rockets are firing, but you can't actually see any flames coming out. Does anyone know why? There's no wrong answers. Anyone? Yes? Combustion, it's actually hydrazine, so I guess it's not really combustion, but it's pretty close. Anyone else like to take a guess? That's also a good guess, but not quite right. Oh yes, we've got another one. There's no oxygen. That's right. The atmosphere is CO2. Any other ones? Oh, sorry.
Is it this hydrogen doesn't burn on a visible light spectrum?
That is true, but the fuel is hydrazine, which is kind of a nitrogen thing. We'll come back to nitrogen, actually. Yes? Sorry? Yeah, but why does that mean you can't see the rockets? Okay, that's a good guess. But you're on the right track. Anyone else? Yes? That's also true, yeah. Does anyone else want to have a go? All right. Basically, you got a couple of answers there that were pretty close. As the gas comes out of the rocket, it expands, right? And because the pressure is so low, it expands an awful lot. And it expands so much that it gets cold, right? If you expand a gas, it gets cold. And if it's cold, it doesn't glow. So it's kind of neat. When SpaceX lands their rockets on Mars, you'll expect to see this huge shooting geyser of flame coming out the bottom. But actually, you probably won't see much at all. And if you watch the videos, you can find them on YouTube, of the Apollo rockets launching from the moon and flying back up to orbit to come home. They also, you see a bit of dust fly out, but you don't see any flames, because by the time the gas expands ambient pressure on the moon is almost nothing. There's nothing that's hot enough to glow anymore. All right, good. Some smart people here. You picked them well. That's good. All right, along the way, I met this badass. Dr. Christine Moran is another PhD in physics. So, 2 physicists, that's dangerous. And then every time we drive past this place in California, we take a photo with our family. And so I named my eldest son Yosemite after Yosemite National Park, and my daughter Sequoia after Sequoia National Park, which is my anchor babies, right? I went over to America. I need to have American names for my American babies. But I just included those to kind of emphasize that, as time goes on, we need to make more humans, but also you get to kind of do that. And we have another one on the way. So, after 2 hours, thanks. It really wasn't that hard. But after, at least, not for me. Arguably Christine's doing most of the work. Kids are fun, man. And actually, my parents are in the audience, so they're up back there. So they got grandkids as well. It's like a win-win situation. They just have to come and visit, to see them. But it's kind of crazy. Like my son is almost 5 now. So he sits down and he asks me stuff, and he says, "Hey, Dad, what's 19 plus 28 or whatever?" And I'm like, 47, and he's like, I think that's right, 57 or something. He's like, "Yeah, that's right." I'm like, "Nice." Anyway, so that's cool. What was I going to say about kids? Kids are cool. Yeah, I can't account for that. Pretty sure that's what my wife's doing. But yeah, it's kind of hard work. Kids are hard work for a few years, and then they get really fun. So after 2 kids, I was like, I'm done, because we were both working full-time remotely for JPL, and we had 2 kids at home, and COVID locked down, and then my wife got promoted to work driving the Mars rover, which was like 12-hour shifts on and off, and then she also got promoted to be like a senior manager, which was like 40 hours of Zoom meetings a week, and it was kind of painful. But then I was like, damage is done. We're going to keep having kids now until they cut us off. So, I mean, like, there's no rule saying you can't have 20 kids. So, anyway. It is possible that they drove me crazy. That's just what kids would do, right? They're like, I'm so cute, you should have 10 more of me. Okay, fine. So this is my garage. It's very important to have a garage if you want to have a startup, because most companies started in garages. Hewlett-Packard started in a garage, Apple started in a garage. This is my garage. It's significantly messier now, but I guess about 2 years ago, I started getting curious about hydrocarbons and what we were going to do about climate change, and we'll talk a bit more about this in a few minutes, but I started here, and have a workbench and a vise and some tools and lawn care equipment and a hammock, and a lab coat, of course, because I'm serious, and started doing, it turns out you can just buy chemicals off Amazon, and just like mix them together. It's actually, so when I was a kid, you could buy dynamite from the hardware store. You can't do that anymore, but you can buy, the sort of stuff that I needed, acids and alkalines and all kinds of stuff, and started doing experiments, and after a few months, convinced myself that it was not a stupid thing to do to quit my dream job at JPL and try something that's really dangerous and really scary in a way. Like, I'm going to be my own boss and have to go and raise some money and hire some people and try, and 99% chance of failure. But raise some money, which is a process, and we leased this building in Burbank. It's a castle. Who here's heard of Skunkworks? Skunkworks is there's one. Skunkworks is the Lockheed Special Advanced Projects division. Doesn't really exist anymore, but back in the day, they built all the big planes you've heard of. So the U-2, the SR-71, the F-117 Nighthawk, stealth fighter, bunch of other things over the years. The P-80 Shooting Star, the first jet-powered fighter in the United States. And Skunkworks is essentially just across the road from us, or where it was, is just across the road from us. So we can go up on the battlements up there, up on the roof, and stare across at Burbank Airport and be like, from this fertile soil, now thoroughly poisoned, it's a super fun site, we can once again develop technology that will pull humanity back from the brink. At least that's how we like to think about it. But we've got 35,000 square feet, and this is the two of the 4 large rooms inside. This one is engineering. This is where all the engineers sit here all together, so we can compare notes and trade jokes and strike gongs and play table tennis together. I put all the flags up on the wall here because we hired a bunch of immigrants, including myself. And then in this room, we are fabricating stuff. So prototypes of machines to absorb CO2 from the air, prototypes of machines to make hydrogen, and prototypes of machines to turn hydrogen and CO2 into fuel. More about that tomorrow. And that's pretty much it for biographical stuff. So how are we going on time? Good. All right. So we're going to talk about energy for a bit here. And first of all, I want to talk about whales in the context of the Industrial Revolution. So who here thinks about the Industrial Revolution on a daily basis? Okay, a couple of people. That's good. A weekly basis? Monthly basis? Who's never heard of the Industrial Revolution? Okay, good. So you might think that I want to talk about whales. Actually, Moby Dick, great book, by the way. Because whaling was a source of oil before we discovered how to use crude oil that we get out of the ground. But actually, whale oil is carbon neutral. It's not particularly renewable, but it is carbon neutral. But no, the reason I want to talk about whales is because, as you can see here in Exhibit A, they have giant mouths. Why do whales have giant mouths? Yes? That's right. Would you like a sticker?
Yeah,
What sort of sticker would you like?
any sticker.
Here, have a Terraform Industries sticker.
Thank you.
I just remembered I had these. I have to ask some more questions. That's pretty close. The reason whales have giant mouths is because they live on food and they need to eat lots of food to live. But that's not unique in that context, actually. All animals do that, right? Except for like some planaria that can photosynthesize. All animals do that. And so we're going to talk about labor and the Industrial Revolution. So before the Industrial Revolution, in pre-industrial societies, some of which actually continued till pretty recently, like here's a color digital photograph of a essentially pre-industrial society. The total mechanical output of these societies, you could think of like their GDP, but for mechanical output, was limited by the digestive capacity of the people who lived there and their animals, but mostly the people, because animals are expensive. And in pre-revolutionary Russia, this is how you move stuff around. Prisoners towing a barge. Actually, the song "Ya-da-da-da" is that. People lived short, desperate lives under conditions of appalling poverty and coerced labor, which kind of fundamentally limited the prospect for human progress, right? If you want to get a lot of stuff done, and the total amount of physical work available to you is just what cranks and stuff people can drag around, which in turn is limited by what they can digest, which in turn is limited by what they can access to, because food was pretty scarce back in the day. Generally speaking, these societies are not that wealthy. Even ancient Rome, even ancient Egypt, right? On average, these societies, on average, had no freedom, right? The people, more than 50% of the population in both these societies essentially had no freedom whatsoever, no access to education. They got to farm. That's what they did. And they farmed by planting plants in the ground by hand. So that sucks. How can we fix it? Steam. Thomas Newcomen in 1712 took steam engines, which had existed in various forms since the time of the ancient Greeks, and used them to pump water out of mines in southern England, which meant that you could dig the mines deeper and longer, and people could work in them without drowning. Definite plus. And actually, the tin mines of southern England had been used since ancient times. There are bronze implements routinely discovered throughout the Mediterranean region going back 6,000 years that use tin that derives from southern England, which is insane. But that's pretty cool. And then James Watt made improvements in 1775, which are very esoteric, and I won't go into them here. But they turned steam engines into practical devices that you could use to do mechanical work, right? Which seems obvious. Why would I be telling you this? You already know this, right? But it's not obvious. Before this time, right, in Robert Boyle's era, 100 years before, if you wanted to grind your grain, if you wanted to sow a field of wheat, if you wanted to run a lathe, if you wanted to make metal, essentially human muscle had to do it, powered by carbohydrates. And after this, you could just feed rocks, coal, which England had no shortage of, into this machine and get essentially unlimited useful work out the other end. Now, the horsepower was invented by James Watt to sell steam engines. And some of you may know that a horse can actually produce about 20 horsepower, right? And it helps to sell you steam engines. If you're like, this one has 20 horsepower, it's like one horse. But of course, horses can't work 24 hours a day. And that's the reason that exists. A strong human, like a Tour de France cyclist, can do 4 horsepower over an extended period, which is insane, but also probably pharmaceutical assisted. So Britain needed no encouragement, right? This is a good thing. Essentially, you can increase the amount of wealth, the amount of productive capacity of your society without starving people, without forcing them to turn cranks harder or longer, by having a machine do the hard work. The machine ran the mills. And of course, environmental consequences, burning coal is not great, but it's better than starving to death in winter. So let's talk about famine. So I unfortunately have a condition which so often afflicts middle-aged men, in which they become obsessed either with World War II or with smoking various meats. And you know what I'm talking about. And so our story here begins, and this story is actually told in gripping detail in this book, The Alchemy of Air, which I recommend to anyone who's interested in these problems. And it begins with this crop of wheat here turning yellow, right? So let's say you're an ancient farmer, and you planted your wheat or your emmer or barley or whatever, and you notice this. It's bad news. Our ancestors knew what this meant. The soil was losing its fertility. They didn't know why. We now know that it's caused by nitrogen depletion. Without exception, this meant hunger, famine, starvation, hard winters, increased child mortality. A few rows of yellow wheat was the harbinger of the collapse of civilization. And without exception, actually with one exception, every single ancient civilization peaked and then died over a matter of a few hundred years at most, because as they expanded agriculture, they depleted nitrogen in the soil until it could no longer produce enough food. And that civilization either had to expand into new land, which they could grow, which would almost inevitably lead to problems that destroyed the Roman Empire, invasion, etc., or starve and collapse. And we know now of dozens of civilizations in which this happened. Some of them invented writing. We know more about them than others. The exception, of course, is Egypt, where annual floods replenished the soil. People were aware of their dependence on natural cycles. People understood this was happening, right? They were not idiots. In many ways, ancients were brilliant. Think about what they achieved with what they had, right? I have a lot of respect for what ancient people were able to achieve, despite the fact that half of them died in childhood. Imagine that. When you people are parents, you'll understand the horror of what I just said. This is a stone that was revealed in the bottom of a river in Germany last year in the drought. And these lines here are carved by people to mark the low water level in historical droughts, 1615, 1100 something, 17 something, going back. Some of these stones say, if you see this, weep, because if the water gets that low, you're going to starve. Right? I don't mean to be a downer here, but let's not romanticize the reality of what the reality of the lived experience of humans for all but the last 100 years, say, at least in this part of the world. And humans have been on the planet for hundreds of thousands of years, and farming at scale for 10,000 years. So nitrogen has a triple bond, which is the strongest in nature. It requires nearly 10 volts to break. And it's fixed in nature by lightning strikes, which are able to tear nitrogen molecules in the air apart and form nitrous oxides, which then rain out into the ocean, into the soil. And by certain plants that have symbiotic bacteria on their roots that are able to fix nitrogen using an insanely clever enzyme called nitrogenase. And 100 years ago, essentially all of agriculture depended on crop rotation, using alfalfa and legumes and so on to fix new nitrogen in the soil with these bacteria, which worldwide had a total of 5 tons of nitrogenase, right? One big bathtub's worth of this particular chemical supported essentially all life on Earth. By the 1880s, it was recognized that a shortage of nitrogen doomed the world to impending starvation. Right, by the 1880s, they understood it was nitrogen fertilization they needed, but they knew of no way to fix it. So they discovered, actually in the early 1800s, that you could use guano, which is bird poo, which is extremely rich in potassium nitrate, which is a fixed form of nitrogen, the N, of course, being the nitrogen in there. Right, so this is a chemical salt. You can dissolve it in water and take off the potassium and add ammonium or whatever. You can just put this on plants and they'll grow like crazy. And there's actually still a law on the books in the United States that any island discovered with guano deposits is automatically annexed by the United States. Other countries may disagree, but most of the islands in the Pacific and the Atlantic that are claimed by the United States are claimed under this law. And in the middle here we have a picture from the guano deposits on the Chincha Islands here, which are off the coast of Peru, that are 50 meters deep. Right, those are some people there, and this is just millennia of birds nesting on these islands, building up with their poo. And this stuff was such powerful fertilizer and also essential for making explosives that in the last days of the age of sail, they built these giant ships. This one here had, I think, 5 or 6 masts that would sail from Europe all the way around the Cape Horn, the bottom of South America, and then up the west coast to these islands, fill them up with this stuff that was packed by forced labor, and sail it back to Europe so they could fertilize the crops and make explosives. And they were so over the top with this that after just 50 years, these islands, all 3, were stripped of bedrock. Imagine that. 50-meter pile of bird shit, and after 50 years, you're at the bottom. So that was kind of a problem. And then later they discovered nearby in Chile saltpeter, which is also potassium nitrate that existed as a naturally occurring salt and was also similarly exploited until it was essentially all gone. And then they're like, shrug, we're kind of out of this stuff. It was still being exploited in the 1930s. And even today, naturally occurring guano and saltpeter are used as fertilizers by certain gardeners. And I have a link here, which I will probably skip today just for timing reasons. But if you type windjammers into YouTube, you can find video film taken in the 1930s of the last of these giant ships sailing around the Cape Horn. It's kind of intense. And they didn't have full harnesses or anything. And they were strong enough, the sailors were strong enough that they could climb up and down the ratlines of the ship hand over hand without using their feet, which was a matter of survival. So, enter synthetic chemistry. This was basically invented in Germany. The German, is that a question? Okay. The German chemical industry, beginning with dyes in about 1890, they developed the dye that makes your pants blue, developed the Haber-Bosch process, which allowed them to produce infinite nitrate for growing plants, and also for bombs, which turned out to be useful for Germany in the First World War, and not so good for the chemical company that developed this, BASF, who lost their patents after World War I. Harsh lesson to be learned there. But this is an engraving, historical engraving, of the Luna plant on the banks of the Rhine. As you can see, it's of enormous scale. And this plant produced hydrogen using electrolysis and captured nitrogen from the air and combined them in enormous pressure vessels about the size of this room at high temperature and high pressure to produce ammonia. Today, half the world's population, 4 billion people, are alive because of this process. Half the nitrogen in your body went through one of these plants. It's pretty neat. Synthetic chemistry part 2. After developing this process in the interwar years, 1920s and 1930s, the German chemists are at it again, and they developed the Bergius process and the Fischer-Tropsch process. I don't expect you to have heard of these, but they're basically the same idea, where you're combining hydrogen with carbon or with carbon monoxide to produce hydrocarbons. In this case, hydrocarbons could include petrol, kerosene, diesel, butane, basically liquids and gases that burn. And of course, Germany had lots of coal, but after World War I, it didn't have any navy and it didn't have any colonies anymore. So it had to find some way of making fuel to run cars and planes and things. You can't run a plane on coal. And so they did it chemically using these processes, which took enormous investment and enormous effort. It's really another triumph of technology. And even today, Germany is rich in coal. And this machine here, which weighs 15,000 tons, that's a pickup truck just down there, that little tiny dot, is chewing up green fields, getting coal out because Germany stopped using Russian natural gas after they invaded Ukraine a couple of years ago. This machine actually makes an appearance in the Avatar film, if you've seen it. And of course, I should mention that this technology was co-opted by the Nazis, as was the rest of German industry, and formed the basis of the Nazi supply of fuel in the Second World War, for better and mostly for worse. And the technology was largely destroyed at the end of the Second World War, although it was still used in South Africa for many years, which also rich in coal and not in fuel. So that's why I included Indiana Jones there, punching Nazis. It's good practice. But this technology has been around for 100 years. And of course, back to airships, no mention of interwar German industry is complete without talking about airships. Pretty cool. So back in the day, airplanes were pretty unreliable and difficult to fly, and engines were not very good, and planes were heavy, and people didn't really know how to make them. But you could make an airship, which just kind of floats. So you have plenty of time to figure out problems if a problem occurs. And they built these absolutely colossal machines. This is the Graf Zeppelin on its first crossing from Europe to the United States. Later, it flew around the entire world. And at the time, planes could fly maybe 100 miles. Right? These things could cross oceans. And so they built this one, the Hindenburg, which is kind of a punchline now, but the Hindenburg made 68 successful crossings before it, over 3 years before it met its untimely demise. One of the few Zeppelins that actually exploded, and actually the only one that exploded outside of wartime use. But it's made of aluminium here, and it was actually blue. This is black and white, obviously, but the aluminium was anodized blue. So it would have been quite a sight to see. This is 40 meters across and 250 meters long, and it could house 200 people, and it could fly across the Atlantic Ocean in 2.5 days, and the fastest ship could do it in 5 days. So until very recently, I think there were still people alive who'd flown on the Hindenburg, which is kind of neat. I think we should build them again. I don't think they're particularly useful or profitable, but they are cool. Okay, let's talk about post-war prosperity. So here's a graph. The numbers are small, but on the left that's 1800, and this is 2000. So 1800 is essentially not much had happened with the Industrial Revolution, and the total amount of energy used, measured in how can I see it here? Kilowatt hours per person per year or something. It was pretty small. It's the blue line. And then starting about 1850, it starts to ramp up as people learn to exploit coal and then learn to exploit oil. And then in the immediate post-war period, it ramps up like crazy, right? Now, in some sense, using a lot of energy is a bad thing because we're burning fuel and it's harming the climate. But in another sense, the fact that humanity is using this much energy is a sign that the number of people in humanity, in the total of humanity who are not experiencing abject poverty in all phases of their life, went from a couple of thousand people to a couple of million people to hundreds of millions of people to billions of people. And today, the number of people who are experiencing dire poverty is less than 1 billion people. Like it's actually a relatively small fraction of the world's population. And there's a good chance that in my lifetime, and certainly in yours, there'll be a thing of the past, which is incredible, right? In my parents' childhood, it was just accepted that the vast majority of the world's population would be hungry most of their lives. Things get better. However, something happened in 1971. This website, WTFhappenedin1971.com, collects about 1,000 charts showing all kinds of crazy things happening there. And basically what happens is this trend of using more and more energy over time stops. And we just kind of held steady. Kind of a period of stagnation since 1971, which is, not that long. My parents in the back were younger than you when this happened. So there's not that many people alive today who remember what was going on back then.
I was born in 1971. Does that count?
No, because you don't remember it.
It could have been me.
Probably not.
It could have been me.
It could have been, yeah.
I don't think so.
Well, if you look here at the price of crude oil over time from 1861, which is, I think, the end of the Civil War in the United States, through to today, in 1971 it starts to tick up. And this is what happened. Oil was becoming scarce and the Arab oil states nationalized their industries and formed a cartel and basically started charging what it was worth as opposed to previously it had been kept artificially cheap. But this created uncertainty in energy prices, which led to a systematic disinvestment in large-scale energy-intensive industries, which we kind of still feel the impacts of today. Like, there's a reason why housing is unaffordable. There's a reason why supersonic planes, we used to have them and we don't have them anymore. There's a reason why we flew people to the moon and the number of people alive who've walked on the moon is small and shrinking, right? And it may improve soon, but it's not going to improve by itself. And in fact, I think that it's my belief, at least, that humanity would have really been in dire straits for the last 50 years if it wasn't for these crew up here, the traitorous 8 who formed Fairchild Semiconductor and later Intel. Because by sheer coincidence, there's no reason this had to occur now or at all, we figured out how to build computers, really powerful personal computers that got twice as good every 18 months. That's unheard of. Right? That never happens. Since when does something get twice as good every 18 months for 50, 60, 70 years? And yet, here we are. And so that allowed us all to make do and to do a lot more, at least in certain areas, with less or with the same amount of energy, which I think it's easy to take for granted. And I would say if I have another piece of advice for you, if you don't already know how, learn how to program computers. Learn how to use Python or C++ or C or Java and become fluent in it. There's this idea that it's this high priesthood of people who work at Google that do it. It's not. It's easy. It's much easier than natural languages. It's much easier than learning to speak another foreign language, learning to make computers work. You can use ChatGPT. ChatGPT can teach you everything you need to know about how to make computers work. If you know how to do that, you're unstoppable because you can summon up a robot army in an Amazon Web Services data center to solve problems for you while you sleep. Right? I know that some of you are probably shit hot at mathematics. Right? You can solve integrals, you can do calculations, you can multiply 6-digit numbers in your head. This phone can do that 1 billion times a second. If you can translate a problem into a series of addition and subtraction steps, you can solve it on a computer, and you can solve crazy, crazy problems that were beyond the wildest dreams of even the academics who taught me. Because when they were younger, they knew about ENIAC and the computers that used tubes to work. They didn't have transistors back then. But everyone has these now. There's no excuse for the future technological elite to not know how to make computers do whatever they want them to do, right? Don't just do no-code stuff. Don't just use a spreadsheet. You actually have to know how to program a computer. There's a thing called the universality or Turing completeness, which basically says that anything that's possible for a computer to do, you can make it do it. Right? And it may take you a while, but you can do it. Incredible problems have been solved this way. Incredible wealth has been generated this way. You people probably don't remember what it was like before the internet. Imagine how life could have possibly have gone on. It's crazy. But we take it for granted, but it doesn't happen by itself. I'm privileged to know and work with people who have been foundational in making this happen, building the world that we take for granted, working at Google, working at Stripe, whatever. And there's no reason why you can't do that. My friend who invested in my company, Dion Ponsini, he worked for Dolby and then he worked for Amazon. He built the Alexa home device. He was on that team, and now he works at Google on internal tooling. And Google, of course, is a huge organization, hundreds of thousands of people, but you know, it's a powerful skill. There's things that I can do with computers that I could not do any other way. All right. New energy sources. So here's a satellite image of my backyard. Well, it's about 2 hours drive from my house, but it's pretty close. And all these black things you can see on the ground, there's some up here, some over here, some over here, some up there, some there, some there, some here, some here. Those are solar arrays. And each of these squares, because United States was surveyed in a kind of sensible way, I believe each of these squares is 1 mile, which is 1.6 kilometers. So like, this is a lot of solar arrays. This is about 2 gigawatts. 2 gigawatts? Yeah, I'm going to say 2 gigawatts in total. And just out of frame, you know, off here, there's about another 6 gigawatts, but it's a bit more spread out. This is exciting. We didn't have this before. I mean, solar arrays have been around since the 1970s, but they're extremely expensive. And now they're the cheapest energy that anyone has ever known. And cheap energy used to be burning coal to make heat, but now coal, you know, heat is low-grade energy. There's only so much you can do with it. You have to turn it into electricity to do cool stuff. This comes out of here as pure electricity, high-grade energy. Slap these guys on the ground, no moving parts, relatively low cost, relatively low maintenance, just produces electricity. Whenever the sun's up, no questions asked, 20, 30 years, no problems. There's a reason that deployment of solar arrays is doubling every 2 years. Right? It's like Moore's Law, but for real stuff. It's crazy. So this is why there's cause for optimism. We're going to solve this problem because of this technology. And actually, Australia has the highest per capita solar generation on Earth. So that's something to be proud of. Here's a graph that I made with a little bit of prediction at the end. So obviously, don't make investment decisions based on this. And this trend actually goes back to the 1960s. But there's a thing called the learning rate, which applies to manufactured goods, things that are made in factories. And it's due to accrued process knowledge, and solar is no exception. And it basically states that every time you double production, the cost falls by a fixed percentage. And for cars, it's about 10%. For computers, it's about 35%. And for solar arrays, it's about 35%. And so this graph shows how, since 2009, solar has gone from an expensive curiosity, you know, so 40 or 50 cents a kilowatt hour, which is actually not too bad in Australia these days, but it was different money back then. And I moved to the United States in 2010. And in 2013, solar got cheaper than gas peaker plants. In 2015, it got cheaper than nuclear. In 2016, it got cheaper than coal. In 2019, it got cheaper than gas combined cycle plants. In 2021, it got cheaper than wind. And in 2022, synthesizing natural gas using solar electricity is cheaper than digging it out of the ground, taking into account all the incentives. And if you follow this curve down by 2029, it'll be cheaper to synthesize fuel, any kind of fuel, from solar power, even in places that are current producers of oil and gas, like the United States, not importers, without any subsidies at all. And there's no physical reason why this curve can't continue down for a good long way. Right? This is $10 a megawatt hour. It could easily go down to $1 a megawatt hour, which is would be down here somewhere. And each of these years you can see, you know, we're doubling roughly every 2 years, but it's actually speeding up recently because for the first time, solar is hitting the big times. Right? It's attracting trillion-dollar investments. It's getting deployed at a fabulous rate. Last year, in 2022, humanity deployed 268 gigawatts of solar power. Worldwide, we have about 500 gigawatts of nuclear power, total. In 1 year, we deployed half that much in solar, and this year we're going to deploy 500 gigawatts, which is on top of what we did last year. There's more than a terawatt of additional solar panel production that's due to come online by 2027 in the United States alone. Right? This is crazy. You never see this in the newspaper. You'll never see it on the television, right? But like, just in the last 10 years, we're about 10 years into a 30-year process, this industry has gone from like, oh, that's cute, to like, holy crap, it's like one of the largest industries on Earth and the fastest growing industry in the history of humanity. So pay attention, right? What careers will you develop which take advantage of this insane resource that humanity's never had before? Per unit carbon, right, so we eat carbon, we eat plants that are made of carbon and water. Solar technology is 1,000 times more productive per unit area than plants. Right, plants are pretty cool, but we can have 1,000 times more energy than we eat. Right now, people in this room are probably roughly 1% of the energy they consume is food that they eat, 99% is gasoline that they burn and electricity that they use in their air conditioners and to run their computers and run their search engines and so on. But we could easily get to another 10x on top of that. What does that look like? It's a crazy future. All right, so I'm getting close to the end here. Is another mid-journey rendering of the 4 horsemen of the apocalypse. Who knows what the 4 horsemen of the apocalypse are? I mean, bad times all round. To quote my friend Anton Tronikov, who also I might add is on the Zeppelin train, technology straight up murdered not 1 but 2 horsemen of the apocalypse. The Haber-Bosch process strangled the breath out of famine, and medical science has rendered pestilence a shriveled husk, a barren of empty halls. Death shows a little more fear in his eyes with each passing year. After all, we've tripled life expectancy in the last 100 years. And even war is cowed because we invented weapons so great and terrible that he himself trembles to wield them, which is also true. The longest and most unprecedented period of peace in human history was the last 70 years, partly because nuclear weapons make it too terrible to wage war. On the scoreboard, humans are doing pretty well, but we're not done yet, and as a teaser for tomorrow's talk, we're going to have to do something about climate. So I'm going to wrap up there, and I'm happy to take questions until I keel over from exhaustion. Thank you.